We built it to answer our biggest questions, to look back to the very dawn of time and piece together the story of our universe. But what if the story it's telling us isn't the one we expected? The James Webb Space Telescope was designed to lock in our understanding of reality. Instead, its discoveries are raising uncomfortable questions. The latest data has confirmed a puzzle that's been growing for years. Our universe is expanding faster than all our models predict, and physicists are starting to wonder if something fundamental is missing from our theories. For a century, we've been telling a single, cohesive story of our cosmos. It's a story that starts with a Big Bang and unfolds over 13.8 billion years, all following a predictable set of rules. We call it the Standard Model of Cosmology. This model has been incredibly successful, predicting everything from the faint afterglow of creation to the vast, web-like structure of galaxies. It's the foundation of modern physics. And the James Webb Telescope was supposed to place the final, beautiful capstone on this incredible tower of knowledge. Its mission was to show us the first infant galaxies flickering into existence, just like our model said it would. But that's not quite what it found. Instead of faint, messy, barely formed galaxies, Webb saw things that, according to the story, shouldn't be there. It found galaxies that were bigger and more structured than should be possible so early in time. And most disturbingly, it has now put a nail in the coffin of a long, hoped-for solution to a problem that's been haunting cosmologists for over a decade. A problem so deep, it suggests the story we've been telling ourselves about the universe might be wrong. So why is what Webb found so disturbing? First, you have to understand the story it was supposed to confirm. We know our universe is expanding. Ever since Edwin Hubble noticed that distant galaxies are all moving away from us, this cosmic expansion has been the central pillar of the Big Bang theory. For decades, we've been on a quest to nail down the precise speed of this expansion. The number that defines it is called the Hubble constant, and it's one of the most important numbers in all of cosmology. If you know the Hubble constant, you can figure out the age, the scale, and even the ultimate fate of our universe. Scientists have two main ways of measuring it. The first is to look at the early universe. By studying the cosmic microwave background, or CMB, the faint relic light from just 380,000 years after the Big Bang, we get a snapshot of the universe's initial conditions. Using our fantastically successful Standard Model of Cosmology, we can then run the clock forward. The model takes those initial conditions, factors in gravity, dark matter, and dark energy, and it spits out a prediction for what the expansion rate should be today. For years, the most precise measurements from the Planck satellite gave a very clear number, about 67 kilometers per second per megaparsec. The second method is to look at the late or local universe right now. This means measuring the distances to nearby galaxies and seeing how fast they're actually speeding away from us. To do this, astronomers use standard candles, objects like Cepheid variable stars and Type 1a supernovae, which have a known, predictable brightness. By comparing how bright they appear to how bright we know they are, we can calculate their distance with incredible precision. For years, the Hubble Space Telescope did just that, led by Nobel laureate Adam Rees. His team's measurements kept coming up with a different number, a faster one, closer to 73 kilometers per second per megaparsec. For a long time, this left cosmologists with a frustrating puzzle. On one hand, a prediction from the early universe said the expansion should be about 67. On the other, direct measurements of today's universe said it's actually closer to 73. This gap became known as the Hubble tension. That difference might sound small, but in cosmology, it's a chasm. It's not a rounding error. It means our universe is expanding roughly 8 to 9% faster than our fundamental model of physics says it should be. For years, the hope was that this was all just a big misunderstanding. Maybe there were tiny errors in the Hubble measurements. Perhaps cosmic dust was throwing off the calculations just enough to be misleading. The community was divided. The tension was real, but it wasn't a full-blown crisis. not yet. That's where the James Webb Space Telescope entered the picture. With its giant mirror and unmatched infrared vision, Webb was the perfect impartial judge. It could see right through the cosmic dust that might have been tricking Hubble and measure those crucial Cepheid variable stars with a clarity never before possible. The idea was simple. Webb would finally settle the debate. It would either find the subtle errors in Hubble's data and bring the local measurement down to match the early universe prediction, or it wouldn't. Adam Rees's team used Webb to re-observe the same stars Hubble had studied. Their meticulous measurements, cross-checked with Webb's infallible eye, delivered a bombshell. Webb didn't resolve the tension. It cemented it. It found no significant errors in Hubble's data, and its new, more precise measurement landed right on top of Hubble's findings. The last hope that this was all a measurement error evaporated. The problem wasn't in our telescopes. The problem was in our theories. As Adam Rees himself put it, with measurement errors negated, what remains is the real and exciting possibility that we have misunderstood the universe.
But the crisis isn't just about one number anymore. The Hubble tension is the headline, but Webb has been finding other, equally puzzling anomalies lurking in the cosmic dawn. It's uncovering a pattern of evidence that suggests our timeline of the universe is, well, broken. When Webb peered deep into the early universe, where our models said we'd find small, chaotic baby galaxies, it found monsters. It discovered huge, well-structured, and surprisingly mature galaxies that simply shouldn't exist so soon after the Big Bang. Some of these galaxies, seen just a few 100 million years after the beginning of time, appear to have as many stars as our own Milky Way, a galaxy that had over 13 billion years to grow. And inside these impossibly early galaxies, Webb is finding another impossibility: supermassive black holes. According to our standard story, black holes are supposed to start small and grow slowly over billions of years. But Webb is finding black holes weighing millions of times the mass of our Sun, just 350 to 570 million years after the Big Bang. They are far too big, way too soon. There just hasn't been enough time for them to grow that massive from a normal starting point. It's a consistent pattern. Stars are forming too fast. Galaxies are getting organized too fast. Black holes are growing too fast. And the universe itself is expanding too fast. It's like we're watching a movie and realizing some of the scenes are playing in fast forward. So, what does this all mean? This isn't just about tweaking an equation. This is a direct challenge to the Standard Model of Cosmology, the theory that has guided physics for half a century. The combination of the confirmed Hubble tension and these impossible early objects points to an unavoidable conclusion. There is something fundamental about the fabric of reality that we are completely missing. Physicists are now scrambling to answer a question that used to be on the fringes of science. What's the missing piece? And the theories are mind-bending. Could there be a new, undiscovered particle in the cosmic soup? Some have proposed a form of early dark energy that gave the universe an extra push in its youth before fading away. This phantom energy could reconcile the measurement from the early universe with the one we see today. Or maybe the answer isn't a new ingredient, but a new rule book. Could gravity work differently on cosmic scales than we think? So-called modified gravity theories suggest that what we see as accelerating expansion isn't from dark energy at all, but a sign that even Einstein's theory of general relativity is incomplete. Some even more radical ideas propose the universe isn't as uniform as we've always assumed. Maybe we live in a giant cosmic bubble or void, where the local density of matter is different, creating the illusion of a faster expansion. Each idea is more exotic than the last, and any one of them would force us to tear out a chapter of our physics textbooks. The James Webb Space Telescope wasn't built to break cosmology. It was built to complete it.
But instead of giving us the final, neat answers we were looking for, it is returned with a beautiful, profound, and exciting new set of questions. The story of the universe isn't over. We're not at the end of the book. We're at the start of a brand new, more complex chapter. The ground beneath modern physics is shaking. The smooth, predictable cosmos we thought we knew is giving way to something wilder, more mysterious, and frankly, more magnificent. And finding out our model is wrong? That isn't a failure. In science, that's the most exciting thing that can happen. It's an invitation to a deeper mystery, a sign that the universe is far stranger and more wonderful than we ever dared to imagine. We are living through a revolution in our understanding of the cosmos. If you want to stay on the front lines of what we're discovering, make sure you subscribe and join us for the next journey into the unknown.